You've probably heard that old rule in the gym, right? To get stronger, you have to get bigger. And look, sure, a bigger muscle is usually a stronger muscle, but that is so not the whole story. In this explainer, we're diving deep into the science of how your body can build some serious strength without adding a single pound of muscle. So let's just get right to it. Can you really boost your strength in a big way without actually increasing your muscle mass? The answer is absolutely yes. And today, we're going to break down exactly how your body pulls off this amazing feat, from your brain all the way down to the tiniest little fibers in your muscles. But first, let's make sure we're all on the same page. When we say strength, we're talking about muscular strength. Basically, think of it as the absolute peak force your muscles can possibly generate in one single all-out effort. In the gym, we measure this with a 1-rep max, the heaviest weight you can possibly lift for just 1 rep. Our goal today is to figure out how to make that number go up. So you might be wondering, why would you even want to get stronger without getting bigger? Well, it turns out there are some really good reasons, and that's what this first part is all about. Okay, so it really boils down to 2 key ideas: relative strength versus absolute strength. Absolute strength is just raw power, who can lift the most weight, period. But relative strength, which is our focus today, is all about being as strong as possible for your body weight. This is absolutely critical for athletes in weight classes, wrestlers, boxers, but also gymnasts, rock climbers, or anyone who just wants to jump higher and be more explosive without carrying extra weight. All right, so to understand how this all works, we have to start our journey at the top. I'm talking about the command center for every single move you make, your brain. That's right. Long before you even touch a barbell, the decision to lift something heavy begins as a little electrical spark in a part of your brain called the motor cortex. This is ground zero for every voluntary movement you will ever make. And that signal doesn't just magically teleport to your bicep. Oh no, it's like this super fast biological relay race. The signal shoots from the brain down what's called an upper motor neuron. It hands off the baton to a lower motor neuron in your spinal cord, and that neuron carries the final command directly to the muscle fibers, telling them, okay, time to contract. And this brings us to a really important concept, the motor unit. See, it's not just one nerve talking to one single muscle fiber. It's one lower motor neuron and the entire squad of muscle fibers it's in charge of. Think of the neuron as a manager and the muscle fibers as its team. When the manager gives an order, the whole team acts as one. And this is where the magic happens. This is our first major adaptation for strength without size. Heavy strength training basically teaches your brain to be a way better manager. It learns how to recruit more of these motor units at the same time, how to send that signal faster, and how to get them all to fire in perfect synchronized harmony. You haven't built a bigger factory, you're just running the one you have with incredible efficiency. Okay, so we've seen the signal zip down the nerve, but how does it actually make the jump, that leap of faith, over to the muscle? Well, that all happens at a critical handoff point, the neuromuscular junction. All right, let's put on our microscopic goggles and zoom way, way in. The very end of the nerve doesn't actually touch the muscle. There's this tiny, tiny little gap between them, and getting the message across that gap is everything. So at this handoff point, you've got a few key players on the field. The nerve releases a chemical messenger called acetylcholine. It floats across that tiny gap, the synaptic cleft, and it plugs into special docking stations or receptors on the muscle fiber. That's what delivers the contract now message. And you guessed it, this is where our second adaptation comes in. With the right kind of training, this whole process gets supercharged. Your nerves get way better at releasing that acetylcholine, and the entire system becomes more efficient at cleaning it up and recycling it for the next contraction. Basically, the signal from nerve to muscle becomes stronger, clearer, and much more reliable. Okay, a message delivered. The muscle got the signal. Now let's go even deeper. Let's see what happens inside the muscle fiber itself to actually create that force. Inside every single muscle fiber, you've got millions of these tiny protein filaments. To keep it simple, let's just think of them as 2 main characters. You've got myosin, the thick one. This is our mover. It's got these little heads that are just desperate to grab on and pull. And then you have actin, the thin one. Think of it like a rope that myosin wants to pull on. But there's a little problem. Myosin can't just grab onto actin whenever it feels like it. There's another protein complex wrapped all around actin, blocking all the good handholds. The source material had this perfect analogy for it. You can think of this complex as the protective parents of actin, always keeping myosin away. So how do we get past these protective parents? Well, that electrical signal we've been tracking, when it arrives, it causes a flood of calcium inside the muscle. Calcium is the key. It binds to those protective parent proteins and makes them change shape, moving them right out of the way. Suddenly, the binding sites on actin are exposed, myosin immediately latches on, pulls in this little ratcheting motion, and then uses energy, ATP, to let go, reset, and grab the next spot. Millions of these tiny little pulls all happening at once, that's a muscle contraction.
And guess what? We can adapt here too, all without getting bigger. Your body gets faster at releasing and recycling that all-important calcium. The actual chemical bond between myosin and actin can become physically stronger. And get this, some of your endurance-focused, slow-twitch fibers can actually start to behave more like powerful, fast-twitch fibers. All right, we have totally geeked out on the science. Now for the part you've been waiting for. How do you actually do this? How do you train your body to make these very specific neural upgrades? Well, here is your blueprint. Okay, let's break this down. You're going to focus on the big compound lifts, squats, deadlifts, presses, the ones that use a ton of muscle at once. The real key here is high intensity, which means heavy weight for very low reps. You also want long rest periods because you need to make sure every single set is a high-quality effort. And finally, tempo is huge. A nice, controlled negative, followed by a conscious effort to lift that weight as explosively as you possibly can while keeping your form perfect.
Now, I really want to hammer this point home, that 2 to 5 rep range. This is your sweet spot. This kind of training is not about getting a pump or feeling the burn. This is about lifting a weight that is so heavy that your nervous system has no choice but to recruit every single motor unit it can possibly find. It is truly a workout for your brain just as much as it is for your muscle.
And that's why the rest is so important too. Taking a full 3, 4, even 5 minutes between sets lets your nervous system completely recharge, so it can go all out on the next heavy set. This isn't about rushing through a workout. It's about making every single rep count to drive those neural adaptations we've been talking about.
Now let's be real for a second. This style of training is incredibly effective, but it does have a ceiling. Eventually, you will max out the efficiency of your nervous system. You'll perfect that motor unit recruitment, and at that point, the only way left to generate more force is to add more machinery, more actin and myosin, and that means increasing the size of the muscle itself. Which leaves us with one final thought. Once you've squeezed every last drop of strength out of your current size, once you've truly maximized your neural efficiency, what's the next step in your journey? How do you make that switch from training for neural strength to training for pure muscle growth? Well, that's a whole other explainer. Thanks for joining me.